Yeah? Okay, so thanks for listening to me. My affiliation is Leuphana University in Lüneburg, which is near Hamburg, northern Germany, and the schedule is that I will have 3 chapters. That is, the first chapter is a review of large language models and how semantics emerge from statistics and syntax. Then is there is the main thesis, that is, it's all about linguistics and how a linguist from last century knew already about very much about large language models' functionality and functioning. And the third is the exotic chapter that shows that this treatment of language is very much like the medieval Jewish cultural technique of text interpretation called Kabbalah. Chapter 1. So the first chapter is about that in 1957, Frank Rosenblatt invented a machine that learns to interpret visual input from a large number of examples. So it does this by using statistics. He called his machine a perceptron, and it became the foundation of all machine learning since then. He wrote himself, "It is possible," and I quote, "it is possible to teach the system to distinguish between 2 shapes by presenting for each shape a random sample from the set of its possible views, while simultaneously forcing the system to respond with output 1 for shape 1 and output 2 for shape 2. And you can see this quite big machine of his, the Mark I perceptron. And so the neurophysiological metaphor has become established in the entire field of artificial neural networks. And what you can see here is a typical depiction of large language models. It supposes that a large language model has something to do with the brain. And I have to disagree strongly about this, and we'll see why. Back to the perceptron. There is a sensory input to the left, such as the grid points of a TV camera. Secondly, the associative level consisting of individual elements that react to the inputs in order to pass them on to their response level, which displays the clear result of the perceptron's activity using just a few elements. The response level of one element indicates a binary decision, square or circle. However, the perceptron does not in no way model a relevant part of a central nervous system, because brain tissue is immensely more complex, as you certainly know. But the nodes, the elements inside those systems, act quite like natural neurons. The inputs are weighted to be more or less strong in activating or damping the signal, and the sum over all signals, and if the sum over all signals is bigger than the activation threshold, the neuron fires like a real nerve cell, as has been discovered in that time. Therefore, this schema shown here is called an artificial neural net. Already Rosenblatt knew the following, and I quote, "The price we pay for using statistical principles in the design of the system is the probability that we will get wrong answer in a particular case." That means a wrong answer that is in the nature of the system and not due to a malfunction of one of its components. And I would claim that this is what we now call hallucinations in large language models. He started with a simulation of the visual part of the brain, but the idea of the whole technology is much more general. So if we have later on, and nowadays, general neural nets, we have very many more associative layers with hidden layers inside. And Rumelhart, Hinton, and Williams achieved the breakthrough in 1986 with a training method called backpropagation. And by the way, they received the Nobel Prize for Physics recently for this. And I quote, "The method repeatedly adjusts the weights of the connections in the network in order to minimize a measure of the difference between the actual output vector and of the network and the desired output vector. Quote end. The rule opens up the possibility of optimizing any artificial neural network so it can perform any task. So from my point of view, the neurophysiological metaphor has now been overcome. The training goes by minimizing the error, which is here on the vertical axis, the difference what the net does to what it should do. And this is an act of interpolation. But if you think of interpolation on data that is not meant to be interpolated, then we get a funny situation. For instance, for non-numerical quantities like language, one could ask the joke question, how to interpolate between a cat and a washing machine, what would come out there? Is it a poodle or is it a food processor? No one knows. But this is more or less the case we have now with the text-generating large language models. So now the technology sketched is used for the following. An artificial neural net can be used for anything. For instance, the input could be a text, not a visual input like a camera image. It could be text, and the output also could be text. Could, for instance, be more text. So we have a neural net that takes text and puts out another text, and it's trained on doing this. And if we generalize this, we have the architecture of the transformer models of nowadays. We have a text, the first word of a text, and it produces the continuation of the text. So the natural large language processor people stole the perceptron idea. Their input now is a piece of text, and the output is prolonged text. The net just has to be trained to do it, and it's perfectly fine with it, to do it on text as it could do it on visual data. So this is the situation now. We start a text, and systems like GPT would prolong them. So inside those machines, we have words that are the inputs. They start as vectors in a 50,000 dimensional vector space. And training is carried out with existing text, man or human-made text. The net afterwards reproduces or is able to reproduce all those training texts word by word. But, and this is where the generation starts, confronted with an unknown text beginning, it would improvise and interpolate between those text prolongations it already knows, and it invents new text. And sometimes it hallucinates. Another glimpse into the inside of large language models is that the words now are squeezed into much lesser dimensions, from about 50,000 dimensions or 100,000 dimensions into something like 1,000 dimensions. So we have a bottleneck, an artificial bottleneck, a sort of abstraction. This is called embedding, as you know. And it would turn out those one-hot vectors with just one and zeros everywhere else into vectors which have a decimal number in each place. Embedding, and this is a very clever thing to do, because now the wonder happens that meaning emerges by this abstraction by scarcity. Words with similar meanings are nearby in the embedding space, which is still 1,000-dimensional or something like that. But if we project this onto 2 dimensions, we can try to visualize these neighborhoods of meaning. For instance, here we have a plot with words that are nearby if they mean if they have similar meanings, and which mean something different if they are far away. Now projected on 2 dimensions, those 1,000 dimensions to 2 dimensions. This is interesting. we can do an algebra of meaning, like king minus man plus woman equals to queen, because we can do this as vector operations, addition and subtractions. And this also works with different languages, so translation becomes possible because these embeddings are similar in similar languages. And if you do an operation in one language, say a path through words on one language, a sentence, you can do the same in the embedding space of the second language. One space is mapped onto the other. This is translation. But now there was another breakthrough in 2017 because the training and the machines now include a layer that expresses relations between words. And this is called the attention mechanism. The attention mechanism outputs the relations between words in the sentences the machine has been trained on. So it is relations of words inside a sentence. And we should keep that in mind because it also will reappear on the linguistic side. Another aspect of large language modeling is that after training with existing texts, those machines would put out everything they have read, and this is not always something that we would like to have. For instance, this training text shows you what happens if the machines are not fine-tuned. They would talk about everything in a quite rude way. This needs then the fine-tuning after the training with the text. So the machine needs to be taught manners now, because it works too perfectly with the trained text. It has read something like this and would now talk like this. Fine-tuning. So the situation with large language models is that there are empirical data. These are those human-made texts, hopefully human-made texts. You know problems about this as well. And on these empirical data, statistics on a big scale is being done. From that emerges syntax, and from that emerges semantics. This is the situation. This was chapter 1. Now we come to chapter 2, which is the main thesis of the talk, that this is not something coming out of the blue, but there is already an existing theory that already brought about these results without computers. And this is the linguistics by Sally Harris, who knew all this or almost everything about what I've just talked about 50 years ago already. So the question is, what is the academic discipline that is the right one to describe all this, what is now happening with large language models? It is obviously statistics as an academic discipline, and it is computer science. But the question is it also neurophysiology? Could we say that knowing something about the brain of people gives us any insight about the functioning and the malfunctioning of large language models? I would say no, it is linguistics. And I'll show you why this is the case. Because the main theoretical assumption by Sally Harris about 50 years ago is the same as with large language models. He said difference in meaning correlates with difference of distribution, and meant is statistical distribution. And actually this is the main point that people in 2010 rediscovered to do semantic disambiguation in natural language processing. That there is the connection between difference of meaning and difference in statistical contribution. And this is called, as an academic discipline, a branch of linguistics, and this is called distributional linguistics. There is a paradigmatic pair of people, Sally Harris and Noam Chomsky. You will have heard of Noam Chomsky, where Chomsky was born 1928 and is very ill now, searched for a minimalist program for a universal grammar that just has to be parametricized in every human then speaking her or his mother tongue. So this is a hierarchical theory that Chomsky always looked for. Harris saw language as a departure from equiprobability. So these are the very different sorts of theoretical approaches. And by the way, Harris, the statistics linguist, was the doctoral advisor of Noam Chomsky. Chomsky made this hierarchical theory as his doctoral student, and Harris made his statistical simulative theory that underpins all large language models nowadays, but this mostly has been forgotten. I quote Harris, "Language has no external meta-language in which one could define its elements and their relations. Hence, the elements can be established only by their redundancies in the set of utterances. That means by the departures from equiprobability in the observable parts of speech and writing, like in the large language models nowadays, which also function solely as departures from equiprobability statistically." And another quote is, "The syntactic theory presented here in his books produces actual sentences of the language with direct indication of their meaning." That is, from this empirical approach, empirical statistical approach, he already saw that syntax would come out. He actually calls this the syntax of the language, and one of his books, 400 pages thick, is called The Grammar of the English Language, which exemplifies all this. And from this also, from the syntax, always comes semantics. And this 400 pages book has elements like this. He tries to note actually spoken parts of language, how this is different from random utterances. He filtered out structures that have a probability greater than 0. He was not able to actually give the actual numerical probability, which we could do now because we have those large language models. He only knew the probability is greater than 0. This is actually being spoken. And this resembles very much the weights in the actual artificial neural nets from nowadays. And for instance, he observed that there is, in the English language, that there are languages like ice breaks rock. And this means that break, the element break, depends on the pair ice and rock. But you could do also more complicated structures, like John hopes ice breaks rock, and he would write it like this: hope depends on the pair of John and break ice rock. And so you get immediately those language trees that you always also would find with Chomsky. But in contrast to Chomsky, these are only the actually observed spoken language elements and their relationships in any actually spoken or written language. Then he made interesting observations on meaning. In the real world, properties or events co-occur with the objects which participate in them. So language and the real world correspond, at least sometimes. But there are words in this kind of type of syntax that are easily interchangeable. For instance, nouns with a concrete meaning, like book, man, place, and words, names. And I quote him, "This makes it possible to form word combinations that go beyond any meaning that could be expressed," in 1991. For instance, if you make a test with those large language models, ask them for your publication list, and you would get invented books and articles, which you never did, but which sound plausible, interchanged objects identifiers. So in this case, meaning does not follow from grammar. These are exceptions. And now comes the quote that electrified me most from 1991. "This is found not only in some schizophrenic talk, but also in imagination, in fairy tales and science fiction, in literary effects, nonsense verse and wordplay. and in various irresponsible discussions. Indeed, one can make a sentence without quite knowing what the meaning is. Schizophrenic talk would be then the key element. And if you have a look in actual psychoanalysis studies, they would confirm this. For instance, the Swiss psychoanalyst Peter Wittmer wrote, in schizophrenia, the ego has withdrawn from the field of appearance. So what actually is schizophrenia? In this form of psychosis, there are only word concepts, not world, but word concepts that are occupied. So this is an existence in words and not in the world. It's the word alone. So a schizophrenic person is in a similar situation like the computers that we are now using for the large language models that do not know the world but just words. And Harris already knew that 50 years ago. That is, I would conclude that hallucinations in large language models are there even a necessary feature, and they are not a bug. They come by design, and I have no hope that they will ever go away as long as we take on these architectures. So we have side by side now large language models and distributional linguistics. We have empirical data. We have processed by statistics, outcomes syntax, and outcomes semantics. So what does that help in interpreting the functioning and malfunctioning of large language models? What could we learn from this perspective? To think of large language models as any sort of general intelligence is outspokenly silly. Or is intelligence completely covered by language syntax? I would not think so. Images or other stuff generated by large language models are only a subset of all images or whatever stuff. They are syntactic images, video or other stuff. Programming languages have a very simple syntax compared to syntax of naturally spoken languages. This is why large language models generate code that actually works sometimes, sometimes not. And if the grammar of the object is different from language, or does not have any grammar at all, and we would claim that there are parts of the word which are not syntactically governed, then we get funny errors. What cannot be represented syntactically in a large language model also goes wrong during generation, like this. There is no anatomical syntax in large language models. What about aspects not included in grammar? For instance, we have voice, the body, consciousness, gesture. Those lack in large language generated text. We know that large language models are weak in logic and in calculation. We know the common errors about this. This is because logic and arithmetic are different and not fully covered by language grammar. And most importantly, since grammar is not equal to truth, large language model output cannot be trusted. Also, and already Rosenblatt knew this and observed it at his perceptron. So that means, from my point of view at least, the neurophysiological metaphor is wrong. Large language models are syntax machines that materialize distributional linguistics. So now I have the third chapter, but time is already very much advanced. So I will only show to you one example of a cabalistic lesson that takes out non-predefined semantics from a text.
Right in the very first verse, you see Bereshit, bara. I've written it up here for you. Et hashamayim va'et haaretz. In the beginning, God created the heavens and the earth. Before we even go on, this first verse is so loaded. What's amazing is if you even looked at this verse, the very first...
I have to shorten this, but that rabbi shows us that in the first word, Bereshit, which could be translated to in the beginning, if you regroup the characters, the Hebrew characters, you get all those words out of it. There is the word son in it, there is the word God in it, thorns, head, gift, and promise, and which easily is the foreseeing of the passion of Christ. So this is a method to milk out semantics of pre-existing text material, and this is, at least for me, very much like how large language models operate nowadays, and which are also, let's say, the cultural reason for hallucinations. So let me just come to my end, and I would say, and put it into a slogan: large language models are linguistic machines that actually automate godless Kabbalah with all the text of the world. Thank you very much.